This is section 19.1, which is about redox reactions, and pretty much this is just a refresher of what you have seen before in 105 or 109. So if you remember, redox reactions are basically reduction and oxidation reactions that happen simultaneously for an overall chemical reaction. Okay, so they happen simultaneously. So there is always an oxidation reaction and a reduction reaction. And just so that you remember, the oxidation is the loss of electrons. If you remember the oxidation number, gets more positive. And in the reduction, when you gain electrons, then that same oxidation number, well, different oxidation number, gets more negative. Okay, one other thing that you have to remember here is that when you look at the reactants in a redox reactions, you usually name them as the agents, the oxidizing agent and the reducing agent. However, one thing that you have to remember is that the one that is oxidized, that becomes the reducing agent. Okay, the way that I like to write this, probably better way to remember is the reducing agent gets oxidized and the oxidizing agent gets reduced. Okay, and all of this is important to remember because now we are gonna study electrochemistry, and electrochemistry is basically the study of the relationship between chemistry and electricity. In other words, electrochemistry allows you to figure out how to harness the power of a chemical reaction for electricity production. So that's what we are aiming for here in this chapter. Okay, so normally, because it's a redox reaction and you have an oxidation reaction and a reduction reaction, then we call them half reactions. Why? Because when you combine them, you obtain your overall reaction, and it all reduces to a transfer of electrons. A transfer of electron between the oxidizing agent and the reducing agent. So one of the things that you need to do to identify each one of these reactions, or what species is being reduced and what is being oxidized, is to determine the oxidation numbers. Right? For any element that is by itself in its most stable form, then the oxidation number is going to be 0. So here for aluminum is going to be 0, and for chlorine is also going to be 0, because even if it's a molecule, is the elemental state for that element, and therefore the oxidation number is going to be 0. Now, when they combine to produce aluminum chloride, then aluminum gets a charge of 3+, and chlorine gets a charge of -1. Now, for ionic compounds and for monatomic ions, for that matter, the charge of the ion is going to be equal to the oxidation number. So here, the oxidation number for aluminum is 3+, or +3, and for chlorine is -1. So let me rewrite this and put it as +3. Okay, so we can describe these half reactions as aluminum going to aluminum 3+. In order for aluminum to go from 0, let me write that down, to 3+, it has to lose 3 electrons. Alright, so think in terms of the charge. So here you have +3, here you have -3. These combined give you a 0, which is what you have on the reactant side. And for chlorine, then same thing. You have 2 chlorines. If you have the element with a subscript because of the formula in your reaction, then you bring that to your half reaction, and then you balance the number of atoms. So you have chlorine here, Cl2s, and then you need 2 chlorines here. Because of the negative charge here for chlorine, then you have a -2 here. So chlorine, to go from 0 to -2, has to gain 2 electrons. So you have a charge of -2 here. Now I want you to focus your attention here on the number of electrons. The first half reaction, you're losing 3 electrons. In the second half reactions, you are gaining 2 electrons. The number of electrons being transferred have to be the same, right? So that means that in order for this to be the same, one thing that you have to do is multiply the top one by 2 and the bottom one by 3. You do that and then you end up with 2 aluminum 0 going to 2 aluminum 3 plus 6 electrons, and then you have 6 electrons plus 3 chlorine 2 Cl2, sorry, going to 6 Cl minus. Okay, so now this number of electrons are cancelled, and then what we do is just to take these coefficients here and you bring them up to your reaction. So that means your aluminum gets a 2 here, your chlorine gets 3 here, and then you require 2 aluminums here, and these 2 times 3 you get the 6 chlorides that you need there. So this is actually the preferred method to balance redox reactions. I mean, this is a reaction that you can easily do by inspection without going through the problem of determining the number of electrons being transferred. But more complex redox reactions will require you to separate it into half reactions. So fortunately, this semester we are not covering how to balance redox reactions. I'm just showing you how it's done. Now in this example we have magnesium with a 0 and oxygen with a 0. Magnesium is going to +2 and oxygen to -2, right? So magnesium is going from 0 to magnesium +2, which means it's losing 2 electrons, and oxygen is going from 0 to 2 oxygens -2. Because you have 2 oxygens here and you are going from 0 to -2, then it represents the gain of 4 electrons. And in doing so, you have to multiply the first half reaction by 2, and the second you just leave it as it is. Alright, so that way you cancel the number of electrons. This is 2 times 2, so there is cancel, which means you have to put a 2 here, you have to put a 2 here, and then you're done. Alright, on the second half reaction, rubidium is going from +1 to 0, and fluorine is going from -1 to 0. Alright, so it's rubidium +1 electron goes to rubidium 0, and fluorine -1 goes to fluorine, we need 2, plus 2 electrons. 2 electrons because you have 2 fluorines and each one is losing 1 electron. Alright, so the first reaction has to be multiplied by 1, the second by 1, the first reaction has to be multiplied by 2 and the second by 1, which means we need a 2 here and a 2 there, and then we're done. Okay, so this is your reduction reaction. This is your oxidation reaction. One special case of a redox reaction is this case of disproportionation. This is when the reducing agent and the oxidizing agent is actually the same substance. It's not the same molecule, but 2 different molecules with the same element. In one case, one is going to lose electrons, and in the other case, the other is going to gain the electrons. So in this particular case, we have the hypochlorite ion that will disproportionate in water to produce the chloride ion and chloride. Okay, so chloride and chloride. Chloride here is -1, the oxidation number. In chloride, the chlorine has an oxidation number of +5, and in hypochlorite, the chlorine has an oxidation number of +1. So in one case, the chlorine is going from +1 to chlorine +5, in which case is losing 4 electrons, and in the other case chlorine is going from +1 to chlorine -1, in which case is gaining 2 electrons. In this case, then the first equation has to be multiplied by 1 and the second you just leave it at 2. Okay, that gives us that you need 2 chlorine +1 +1 chlorine +1. Let's keep it that way for a moment, right? And then you obtain 2 chlorine +5 +1 chlorine -1. Okay, so these are the same, so you end up with 3 chlorine +1. Okay, so you put a 3 here. You put, let's change the color here. You end up with 3 for hypochlorite, with 2 for chlorate, and then these just stay at 1. And that is your balance equation. So in this case, the chlorine +1 is the reducing agent and the oxidizing agent at the same time. So in these two reactions, okay, identifying the oxidizing and reducing agents in this reaction, well, pretty much if you only have one reactant here, that would be the case. That is the same, the oxidizing agent and the reducing agent. But just for the fun of it, let's write our equations, right? So in here in nitrous acid, we have that nitrogen has a oxidation number of +3. In nitric acid, that is +5, and in nitrogen monoxide, this is +2. Okay, so nothing to really look for in the other things. Hydrogen and oxygen keep their own oxidation number, so I let that up to you to figure that out. So we have nitrogen +3 going to nitrogen +5 +2 electrons, and then we have nitrogen +3 going to nitrogen +2. In order to do that, you have to gain 1 electron, which means the first reaction times 2, the second reaction just 1. Alright, that means you will have a combined 3 nitrogen +3 going to 2 nitrogen +5 +1 nitrogen +2. So your balancing numbers are 3 nitrous acid, 2 nitric acids, and then just 1. Now in the second case, we have chlorine with a 0 as a good oxidation number, and sodium is always combined, so sodium always will have a +1 all around. And here oxygen and hydrogen, whenever they combine, they always have -2 and +1 respectively. So here the issue is with chlorine, that is going from 0 to -1 and to chlorine +5. Okay, so our half reactions are Cl2 0 going to Cl-. In order to do so, and we have to add a 2 here. In order to do so, is each chlorine is gaining 1 electron, so we need 2 electrons here. And in the second case, chlorine is going to 2 chlorine +5. In order to do so, from 0 to 5, you are losing 5 electrons. You have 2 chlorine, so this is 10 electrons. Okay, so that means the first reaction you have to multiply by 5, and the second reaction you can leave it as it is. That will give you a combined 6 chlorine 0 going to 10 chlorides and 2 chlorine +5, which means all you have to do here is add 6 at the chlorine, you have to add 10 here, and then you have to add 2 here, and then technically you have to balance with the rest. Alright, so in review, remember, a redox reaction can always be separated into two half reactions. One represents the oxidation reaction and the other represents the reduction reaction. Okay, you have to combine both half reactions, but you need to try to balance the number of electrons being transferred, because you are not getting electrons out of thin air, and there will not be electrons floating by themselves after the reaction. So the same number of electrons that are being lost is the same number of electrons that will be gained by another species. Last but not least, the disproportionation is still a redox reaction, but in this case the reducing and the oxidizing agent is the same substance. Not quite the same molecule, so you have two different molecules of the same substance. One will undergo a reduction and the other will undergo oxidation. Okay, so this is the refresher for redox reactions, and then we will move into voltaic cells. We will not fully cover the balancing of redox reactions.